All right, thanks. Great. So rather than spending a whole lot of time talking about our recent workshop, I think I'll probably talk quite a bit about that next year's peer meeting, since we're kind of still wrapping up a report. I want to talk about another peer-funded project that was approved in 2020 that has been undertaken by my former student, Ali Dadashi Saraj. So this work is largely his, and thank you, Ali, for joining us today. The objectives of this study was really to provide a means to estimate cyclic strength or cyclic resistance in the absence of site-specific cyclic laboratory testing. And this kind of information could be leveraged perhaps directly into some of the models that the NGL modeling groups may be interested in developing. But the idea is providing estimates of cyclic resistance that could be used with a simplified method, perhaps planning a site-specific laboratory testing program when you might be rather unfamiliar with where to start with the CSR or the number of equivalent cycles, as well as calibrating constitutive models or performing site response analyses. Additionally, we wanted to identify cyclic resistances that are strain dependent. So different projects may have different criteria for allowable deformations or different thresholds on risk, providing limits on strain that can occur for a given number of loading cycles we felt was of interest. Hand in hand with this is understanding just how many loading cycles are possible and appropriate for soils that may exhibit low or moderate plasticity. So, you know, the first lens through which we viewed this work is through the simplified method, which was proposed for cyclic softening circa 2007 or so. But just like with liquefaction triggering, we're looking at the most basic level at the ratio of capacity to demand. So the cyclic resistance for which the models we've developed with provide the numerator in this expression, whereas the loading may be coming from the typical formulations for the simplified method, where we might take 65% of the peak shear stress normalized by the vertical effective stress. It should be pointed out that whereas in other decades, the peak pore pressure of 100% might be used to identify initial triggering of liquefaction, we've seen the profession move to a shear strain-based cyclic failure criterion, typically selected as about 3%. So we can tune that dial to select the cyclic failure criterion in terms of shear strain that we like, depending on the risk. The other thing when we want to think about the simplified method for cyclic softening is that the shear stress reduction factor has really been developed largely for liquefaction triggering models, not so much cyclic softening models. So clearly this is an area of further research that needs to be addressed, not just for cyclic softening, but for large magnitude earthquakes such as that here in the Pacific Northwest with our Cascadia subduction zone earthquake. So that brings us to the underpinnings for statistical models. We have developed a suite of sites that OSU has investigated. They're distributed geographically, as shown here in the figure on the right. In some instances, we've been able to couple our samples and cone penetration soundings with in situ dynamic testing. We like to use controlled blasting up here, so we've done that at a couple locations. And at one location, we have had the benefit of the vibro-sized shaker truck T-Rex that we brought up from UT Austin. So all of our, the majority of our specimens will be drawn from these test sites, but we've also supplemented with a series of cyclic test data performed by consultants. So there's quite a lot of information on this table. I just want to point out that for our data set, the PIs are generally ranging from non-plastic silty sands to sandy silts, so a PI of 0 on the upper end to a PI of about 40 or so. And the natural materials, that is representative of the stresses in the deposit from which these specimens came, have overconsolidation ratios that generally range from 1.5 to 4. We did take some number of our intact specimens to an artificially induced normally consolidated stress state so that we could identify a potential lower bound on cyclic resistance for those materials, which would then inform our statistical models. So I've plotted here the breadth of data that we have in our testing data set. And at first glance, you can see that the variation of the cyclic resistance with the number of loading cycles is really quite large. There's a lot of variability here. Naturally, the contributions of things like plasticity or stress history, natural soil fabric contribute to this variability. And so we use statistical regression analyses to try to tease out the various contributions of potential predictors on cyclic resistance to inform and underpin the estimates of cyclic resistance that we'd like to make. So that brings us to our statistical models, and we've developed a suite of several models. I'm just going to focus, though, on a model to estimate the exponent B in the variation of cyclic resistance with the number of loading cycles. This is a form of a power law in which B prescribes essentially the slope of that power law in the CRR-N space. We've developed a series of strain-dependent models for cyclic resistance ratio or cyclic strength ratio if undrained shear strength is available and can be used to peg your cyclic resistance to. I'll talk about one of our strain-dependent CRR models that we've developed. And by virtue of demonstrating maybe the significance of some of the models, I'll talk about our variation of equivalent number of cycles for our subduction zone ground motions. But the procedure that we followed was essentially a staged regression analysis in which the first stage, we just want to identify significant predictor variables and the basic functional forms which might be statistically significant over the range and strains identified. Again, we're only considering intact specimens that are largely undisturbed. I think intact is a better term for that because all samples have some amount of disturbance. And these were all sheared under in situ stress conditions with the exception of those taken to an NC state in order to identify that lower bound. And so we first subdivide our data into a training and testing data set. We confirm the suitability of our models, and then we go and develop the final statistical model using our full data set. So talking about our first statistical model that could be useful, which is the model for exponent B in the CRR-N curve. We can see that void ratio has a relatively strong correlation to exponent B, so does plasticity, but stress history doesn't seem to really control the curvature of the CRR-N curve. And so we disregard stress history for this particular model. However, as you can expect, the void ratio and plasticity index are strongly correlated. And that's just natural because as the degree or the amount of clay minerals increases, the aspect ratios of these particles increases. We begin to see more rod and cone-shaped type clay minerals. And so we just tend to have larger void ratios and void spaces as a result of the introduction of these clay-rich minerals. And so we need to be cognizant of this correlation and make sure that we don't introduce multicollinearity in our statistical analyses. So here's an example of the exponent B model that we've developed. It's a simple linear term of plasticity index. We decided to use plasticity index because you can develop that soil characteristic index from split spoon samples, which are highly disturbed, as opposed to intact samples that you need to estimate the void ratio correctly from gravimetric water content and volume calculations. We can assess the goodness of fit with things like the point bias. It's simply the ratio of measured to estimated exponent B in this case. We can also look at the variation of the point bias in terms of the coefficient of variation or the standard deviation divided by the mean point bias. And what we see is that the training data seems to have produced an unbiased estimate of exponent B with a coefficient of variation just under 20% or so. But that functional form seems to maintain its robustness with our testing data set. And so that gives us some confidence to move forward and develop the final model shown in the blue equation in the upper right. And we can see that it produces a relatively unbiased estimate of exponent B with coefficient of variation of about 18%. Now, why this is important for a couple of reasons. For one thing, based on the very limited data at the time of about 2006, 2007 or so, when the original simplified method for cyclic softening was proposed, it seemed that a single value of B of about 0.135 was appropriate for 30 cycles of loading and a cyclic failure criterion of 3%. However, you can see that there really is a notable variation in this curvature of the CRR-N curve with plasticity. So we need to account for that because it does impact the number of loading cycles that you would select ground motions for in your analyses. So if the exponent B drives the curvature of the CRR-N curve, well, now PI drives the exponent of the CRR-N curve and therefore the number of loading cycles. So we can assess the effect of exponent B on the number of equivalent cycles. And we see a couple different trends. I've got two examples here for a B of about 0.1. That's typical of our low plasticity silts, and a B of 0.34, which might be more typical of clean, medium dense to dense sands. When we've got these relatively shallow CRR-N curves, there's a much more muted variation of the number of equivalent cycles with magnitude as compared to that with sands. So this is one area in which the simplified method for cyclic softening is going to be somewhat different than that for liquefaction triggering. The other thing I'd like to point out is the significant variability in the number of equivalent cycles for a given exponent B. So if we look at a typical exponent for low PI silts of about 0.1, depending on the ground motion, you might see a number of equivalent cycles vary from something like 35 to 275. And that's got a lot larger range than we might have expected. And certainly the average, at least for the Nisqually earthquake, which was a magnitude 6.8, here in the Cascadia subduction region, you've got about 75 number of cycles. And so that's a big departure from what we might have seen in the original formulation. Looking at larger magnitude earthquakes, like the expected 3 to 5 minute duration full rupture of the Cascadia subduction zone associated with a magnitude 9 or larger, we might have 93 cycles of loading expected on average, but also, again, we have to recognize that uncertainty. So this could be useful moving forward in making your cyclic softening assessments. The other model I wanted to talk about was that for cyclic resistance, first at 3% shear strain and then as a function of strain. Again, first we just see which variables appear to be statistically significant. Void ratio and plasticity index and stress history all appear to be relatively weak predictors of cyclic resistance. The number of cycles clearly is a lot larger. But we wanted to assess the univariate effect of these variables before we put together a nonlinear model. But although we've got this relatively weak to moderate correlations, all of these variables are statistically significant. And so we need to tease out the relative contribution of these variables on cyclic resistance. And after many trials and assessments, we came up with the functional form that you see here, where we've got the plasticity index and the overconsolidation ratio. Again, we passed on void ratio because it's easier to get to PI. And the fitted coefficients and exponents are all statistically significant and provide relatively unbiased estimates of cyclic resistance across all N, with a coefficient of variation of about 17% based on the training data. The strength of this functional form appears to be upheld with our independent testing data. And so we select this functional form for our final model, which produces an unbiased estimate of cyclic resistance with a coefficient of variation of about 16%. So let's take a look at what kinds of estimates of cyclic resistance or trends in cyclic resistance we can see as a function of plasticity and stress history. As you can expect, the higher the stress history, the larger the cyclic resistance. I've got OCRs of 1 and 2 shown here with PIs that range from 0 to 40. Naturally, non-plastic materials have a lower cyclic resistance than plastic materials. And as we go from a PI of 0 to 10, we see a fairly large increment in cyclic resistance. But as we begin to increase in plasticity beyond 10 or so, we see that there's reducing increments in the gain of cyclic resistance that you can expect. Nonetheless, if you're interested in the cyclic resistance at a given number of loading cycles, this model provides an estimate of that cyclic resistance at 3% shear strain. We also evaluated cyclic resistance at shear strains ranging from about 0.5 to 10%. It's really quite difficult to evaluate cyclic resistance at strains lower than 0.5, at least in the devices that we use, because these plastic materials are relatively weak and shear strain accumulates much more rapidly than it would for clean sand type materials. But the functional form that we used for this strain dependent model did use the same functional form as at 3%, and all of the model parameters, that is the fitted coefficients and exponents, remain statistically significant across all shear strains. One of the notable things here is that the number of specimens that we can use to train our data fell off real sharply after a strain of about 3 to 3.75%. And so the quality of the CRR estimate clearly falls off for these really large strains, but we expect that as we continue to build our database, that we can slowly converge to the quote unquote true model parameters for this particular functional form. But here you can see how the cyclic resistance now might vary as a function of shear strain. And I've got 30 and 100 loading cycles shown here. This could be rather useful for calibrations of your models for site response analyses or constitutive models, as well as for planning your laboratory test program. Importantly, we think that we can now move towards maybe a performance-based simplified method for cyclic softening procedure in the future, which I think is really something of interest for the peer community. And we think that these kinds of models can lead into that. So I think I'm getting close to the end of my time. I think the talk is short enough. I don't need to go through some of our conclusions, but we do think there is a broad application for these kinds of relatively simple statistical models that could help advance the practice for making assessments of cyclic softening, even perhaps interpreting some of the case histories that Scott discussed in the presentation before this one. And we're continuing to do work with our database by working on the development of some G by G max and damping curves over a fairly large range in strain, pushing the strain boundary for these silt materials than for some of the models that are currently existing. So with that, I'd like to thank Ali Dadashi, the former student who helped develop these models, the peer group for their funding, as well as the other sponsors contributing to this data set. So thank you, Ada. I'll turn it back over to you.
Thank you, Armin, very much. Any questions for Armin?
I have one if I'm allowed to ask. I'm not there in person, so I should defer to the people who are actually there. But
sure, go ahead. Go ahead, Scott.
Oh, okay. Thanks, Armin, for a really nice presentation. One thing I noticed in your data is that you have an exponent on the OCR term. And a lot of the time people just think that cyclic strength is proportional to monotonic strength, in which case that exponent should be somewhere around 0.8-ish. But I saw that yours was down around 0.3, which is something that I've also found in some data that or some soils that we tested. So I'm just curious about that exponent. Are you seeing less of an effect on cyclic strength than on monotonic strength in these soils?
Yeah, that's right. And also, there's interaction between the predictor variables, right? So now clearly you wouldn't expect PI to be correlated to OCR, but perhaps the depositional environment from which these specimens came might be characterized with some kind of common stress history. But for sure, the strength of OCR as a predictor on cyclic resistance is weaker than you'd expect from the more or less single variable Shansep type model for undrained strength. So I think that's interesting, your observation, and certainly we should explore that offline at some point.